Alright, so in this video we go over section 7.5, which is the sum and difference formula. So in this case we're going to use the sum and difference formula. In this section we're going to use difference formulas to find the exact values of some trigonometric expressions, and then use these difference formulas and some formulas that involve inverse trigonometric functions, some of the compositions, just like we did in the previous couple of sections, and then solving the trigonometric equations. I'm going to leave it for the end of this chapter. All right. So, let's look at the sum and difference formulas for cosines. Let's start with cosine first. So if we have cosine of a sum of angles, this is the same as writing it as cosine. Well, in this case, those two angles, alpha and beta. This is the same as writing cosine alpha times cosine beta minus sine alpha sine beta. On the other hand, for the difference formula for cosine, this is exactly the same formula as above, but with opposite sign. Notice a good pattern to recognize is that cosine of the sum involves a difference and cosine of a difference involves a sum. All right. So let's find the value of the values of the following. Well, like cosine of 15 degrees. Well, one of the disadvantages of using the unit circle is that the unit circle contains values only for angles that are 30 degrees, 45 degrees, and 60 degrees. And of course, there are multiples that lie in the remaining of the quadrants throughout spanning the entire Cartesian plane. But in this case, to evaluate cosine of 15, if you try to look for cosine of 15 in the unit circle, it's like I mentioned, it's not going to be there. Only 30, 45, 60. Well, 15 would be somewhere here, but we don't have the information. Nevertheless, we are going to take advantage of number one, the formulas above, with a couple of tricks, and then we are going to use those values. You'll see. So the trick here is for cosine of 15 degrees, we're going to write cosine of 15 degrees as 45 degrees minus 30 degrees. All right. Why am I choosing those numbers like kind of randomly? Well, they're not really random exactly. I would like to write this 15 as the sum or difference of two numbers that are related to values in the unit circle that we can relate to. All right? Because of course we could have say 20 minus 5, but 20 is not in the unit circle, 5 is not in the unit circle, so we need to write those in values that are in the unit circle. So then we're going to use, in this case, the cosine alpha minus beta, and then that formula because we have a minus inside, so that's going to be cosine of 45 degrees cosine of 30 degrees, and then plus sine 45 sine of degrees and sine of 30 degrees. And then from here, all we have to do is use the unit circle to get those values. Cosine of 45 degrees, cosine of 30 degrees. So cosine is the x value. Cosine of 45 is square root of 2 over 2. Cosine of 30 degrees is square root of 3 over 2. So I'm going to multiply these two values here. So cosine of 45 degrees is square root of 2 over 2 times cosine of 30 degrees, which is square root of 3 over 2, plus sine of 45 degrees. Well, sine is the y coordinate, and then sine of 30 degrees, which is the y coordinate of this point. That's square root of 2 over 2 times 1/2. Alright, in this case, all we have to do is simplify this. Multiplying across the radicals, in this case, 2 times 3, all we have to do is write it as the square root of 6 over 2 times 2, which is 4. And then the square root of 2 times 1, that's simply the square root of 2. And then in the denominator, 2 times 2 is 4. And all you might want to do is simply combine the square root of 6 plus the square root of 2, and then divide that by 4. Final answer. That's an example of how we use this cosine difference formula. Okay, let's do another example. In this case, well, cosine of pi over 12. Well, again, we have pi over 6, pi over 4, pi over 3, but we do not have that pi over 12, right? Okay, so what's the trick over here for cosine pi for pi over 12? Number one, the trick here is to write this cosine of pi over 12 as cosine of, well, in this case, I'm going to write this as 4 pi minus 3 pi over 12. Well, where did I get that 4 minus 3? Well, because number one, 4 pi minus 3 pi equals 1 pi. But where did I get this 4 minus 3? Why I didn't do 7 minus 6 or 59 minus 58? You know, well, in this case, the reason why I chose this 4 and 3 is in a way that those numbers have common factors and they reduce to nice numbers like having 4s as denominators or 3s as denominators or 6s as denominators. So what are we going to do here? Well, I'm going to split this up into 4 pi over 12. That's going to be cosine of 4 over 12. Isn't that pi over 3? That's pi over 3. 4 goes into 12 3 times. Minus 3 pi over 12, that's a 3 over 12, that's a pi over 4. Alright? And then from here we are going to apply the formula for this. In this case, again, we're going to apply the difference formula for cosine. That's going to be cosine pi over 3 times cosine pi over 4 plus sine pi over 3 sine pi over 4. It's kind of hard to read. Hopefully not that bad to read. Okay, that's a times. Okay, I didn't put parentheses otherwise, so it fits. Alright, so now we're going to use the unit circle to evaluate this quantity, cosine pi over 3, cosine pi over 4. So cosine is the x quantity, cosine pi over 3, that's 1/2 times square root of 2 over 2. And then plus sine pi over 3, sine pi over 4, sine pi over 3, sine pi over 4. Very, very similar to what we did earlier in the previous example. So that's sine, that's, what was that? Root of 3. Root of 3 over 2 times root of 2 over 2. Okay, so this will be root of 2 times 1, that's root of 2 over 4 in the denominator, and plus root of 3 times root of 2, that's root of 6 over 4. And well, combining these two together, that's going to be root of 2 plus root of 6. Actually, it's the exact same result as in the previous example. It was just given in a different format, given in a different way slightly. Alright, let's look at sum and difference formulas for the sine function. And they're kind of similar, of course, just be careful when looking at the patterns. The cosine formulas involve cosine, cosine, sine, sine. Cosine, cosine, sine, sine, and then interchanging the signs. Positive, it goes to negative, negative goes to positive. However, for the sum and difference formulas for the sine function, well, the plus remains plus, the minus remains minus, but these are these are, you know, like kind of mixed up. So sine of the sum is sine alpha cosine beta plus cosine alpha sine beta. So there's some interchanging in there. Same pattern, but just opposite sign afterwards. All right, so let's look at one example of what to do in a situation like this. Well, so for sine of 19 pi over 12, well, that number might look a little bit kind of ugly to break up. Yes, I agree. But don't worry, we're gonna figure it out. We're gonna find a way to express that 19 as a sum of nice numbers. Well, I'm gonna do actually sine of the sum. And well, you might be asking, where did I get this from? Well, this is 15 pi plus 4 pi, all right, over 12. Why those numbers? Well, I mean, of course, we could have done 20 over 20 and 1. I mean, 18 and 1, but 18 and 12 and 1 over 12 is not going to reduce to nice numbers in the denominator to have 3s, 4, and 6. So we can use the unit circle. In this case, if we divide 15 over 12, that's going to give us 5 and 4. And over here, 4 over 12, that's going to give us 1/3. All right. So let's use the sine formula for this. Let me put it up here. So in this case, sine alpha plus beta, that's sine alpha cosine beta. First, I need to establish what alpha is and what beta is. So this is sine 15 pi over 12 plus 4 pi over 12. Okay, this reduces to 4 pi over 4. Over 5 pi over 4, rather, not 4. 5 pi over 4. Let me fix this so it doesn't look ugly. 5 pi over 4 and plus pi over 3. All right, and then I'm going to use the formula of the sum for sines, which in this case is sine of 5 pi over 4 cosine pi over 3. All right, in this case, keep in mind this is alpha, this is beta. This is alpha, this is beta. Alpha and beta. Okay, and then plus cosine of alpha, which is 5 pi over 4, sine pi over 3. Again, that's alpha and beta. Alpha and beta. Alright, so all we need to do is simplify this using the unit circle. Let's get those values. 5 pi over 4, where's 5 pi over 4? So we're going to do sine of 5 pi over 4, which in this case 5 pi over 4. Sine is negative root of 2 over 2. Times cosine of pi over 3. Cosine of pi over 3, that's 1/2. And then plus cosine 5 pi over 4. Cosine 5 pi over 4, that's a negative root of 2 over 2 as well. Times, in this case, sine of pi over 3, which is root of 3 over 2. Okay, so let's just simplify this by multiplying across. This is negative root of 2 times 1, that's a negative root of 2 over 2 times 2, which is 4, plus negative, well, minus, that's a root of 2 times root of 3, that's root of 6, over 2 times 2, which is 4. And then, well, we can actually simply combine this together as negative root of 2 minus root of 6, the whole thing over 4, or factor out the negative sign. Either way is fine. Okay. Alright, so for the next example, part B of this example 2, well, we are looking at the formula in a backwards form. So we're given the pretty much something that looks like the right hand side. We're gonna combine it together. Well, in this case we see in this case this is alpha, this is beta, alpha, beta. In other words, alpha equals 80 degrees and beta equals 20 degrees. Okay, so in this case, notice that we have the one with the minus sign. That means we need to do the minus. Okay, so this is sine of alpha minus beta, and in this case sine of alpha, which is 80 degrees, minus beta, which is 20 degrees. 80 minus 20, that's sine of 60 degrees. And what's sine of 60 degrees? Sine of 60 degrees is the y-coordinate in the point in the unit circle, root of 3 over 2. Alright. Okay, now let's move on to kind of a different type of exercise in which we will put together what we know from what we have from the previous few sections and put it together with this section. Well, number one, the way this is given, it's like they're like giving us a lot of information. We're gonna put it, we're gonna break it up into pieces, and then in the end have everything together. All right. So if sine alpha equals 4/5 with pi over 2 less than alpha less than pi, well, kind of hard to read. Well, that's not how we read it anyway. And sine beta equals negative 2 over root of 5 with pi less than beta less than 3 pi over 2. Find the exact value of each of the following in the ones that are here below. All right, number one. Well, here I have two Cartesian planes with a circle. The first one I'm gonna call this for alpha, and this is gonna be for beta. All right, sine of alpha with pi over 2 and pi. This is, in other words, this is telling us that second quadrant. And pi to 3 pi over 2, this means third quadrant. That's what this means. Alright, so it means that we need to plot the point in which sine alpha equals 4 over 5. That is, keep in mind, one thing to keep in mind is that sine let me put alpha to go with it, is y over r. Alright, so that means we're gonna go to, and in this case, well, what is the sign of cosine? Well, we're gonna figure out what cosine is in this quadrant. Well, it's negative, so I'm gonna go with y equals to 4. Y equals to 4. And okay, let me check my notes real quick. And okay, so we're looking for some point where x is to be found, comma 4. All right, and this has a radius of r, which is 5. So we're gonna figure out what x is. R squared equals x squared plus y squared. And r squared is 5 squared equals x squared, which is the one that we need to figure out, plus y squared, which is 4 squared. 25 equals x squared plus 16. Subtract 16 to both sides. X squared equals 9, and x equals plus minus the square root of 9, which is plus minus 3. In this case, well, I put the plus minus sign. However, in this case, we take the negative. The reason why we take the negative is because x is negative, so it's going to be negative 3. All right. Now let's do the same for beta. Well, for sine, we have sine beta. Well, again, recall that sine, it's also y over r. If we were given cosine, like you will be given in other exercises, and when you do the homework, well, sine beta, a cosine would have been x over r. But in this case, we're also given sine beta. All right. So let's see. Sine beta. In this case, keep in mind that this is going to lie in the third quadrant. So I'm going to go to a place where, in this case, y is negative 2 and r is always positive root of 5. Okay, so I'm going to look for a point where r equals to root of 5, and the other pair, the point is something comma negative 2. Of course, this is going to be a negative number as well. All right, so we're going to figure out that value. So r squared equals x squared plus y squared. R squared, which in this case is root of 5, quantity squared, equals x squared plus y squared, that is negative 2, quantity squared, and in this case roots cancel, leaving us with a 5. X squared plus 4. Subtract this on both sides. Subtract that on both sides. And what are we going to get? Well, x squared equals to 1. X equals plus minus the square root of 1, which is plus minus 1. Of course, if we use the square root property, we have to use the plus minus sign. However, in this case, the direction of x in the third quadrant is towards the negative, so that's why we take the negative. All right, so I think we have everything we need. It would be a good idea to list everything. Okay, I'm going to use a different color, x, y, and r, just so it doesn't look messy. So x equals negative 3, y equals to 4, and r equals to 5. Likewise, I'm going to do this over here. X equals negative 1, y equals to negative 2, r equals to root of 5. This three-number summary, if we will. Okay, so what's cosine of alpha? So keep in mind that we're looking for alpha, that is the first diagram. So cosine, which is defined as x over r, that's simply negative 3 over 5. Final answer. Cosine beta, well, again, it's also x over r, but in this case, the x and the r from the second diagram, because they're asking us for beta. Beta, that corresponds to the second diagram. And in this case, that's x, which is negative 1 over r, which is root of 5. And again, you might want to rationalize the denominator in this case. Of course, maybe my MATLAB might be a little bit picky about it. Just in case, let's rationalize them. Negative root of 5 over 5. Alright, so let's look at cosine alpha plus beta. Well, in this case, you might want to revisit the formula. Cosine alpha plus beta is cosine alpha, cosine beta, sine alpha, sine beta with a minus sign in between. All right, let's write down the formula if possible. Cosine alpha, cosine beta, minus sine alpha, sine beta. Okay. Okay, now what's cosine beta? Cosine beta, we already had it from the step before. I mean, cosine alpha. Cosine alpha, that's negative 3/5, right? That's negative 3/5. Cosine beta, that's from the previous step as well. That's negative root of 5 over 5. And then minus sine alpha, sine beta. Well, sine alpha was given, and so sine beta, all we have to do is copy these two values. 4/5, which is sine alpha that was given, and then sine beta, which is also given, that's a negative 2 over root of 5. All right. All we have to do right here is simply put everything together. Well, the denominators, well, actually, it would be a good idea if we rationalize this this denominator. You know, you may not want to have radicals in the denominator. Well, so that's well, let's multiply this negative times a negative. That's positive 3 root of 5. 5 times 5, that's 25. Negative times a negative, it's positive. Well, 2 times 4, that's 8 root of 5 over root of 5 times itself, that becomes simply 5. 5 times 5, that's also 25. And in this case, well, that becomes one single fraction because we have the same denominator. 3 root of 5 plus 8 root of 5, all we do is add the coefficients 11 root of 5. And that's final answer for this example. All right. For the next example, for the last part of this example, it's something similar. Well, we're going to use the formula for sine alpha plus beta, which is right here. Let me copy it down. Sine alpha cosine beta plus cosine alpha sine beta. Okay, well, sine alpha. Sine alpha, again, it was given in the problem. Sine alpha is 4/5. Cosine beta, we figured that one out over here, negative 5. Actually, negative root of 5 over 5. Plus cosine of alpha, that was also, we figured that out as well. Negative 3/5. And sine beta. Sine beta was given, all right? Negative 2 over root of 5. It's basically the same as here. So that's a negative 2 over root of 5. And you might want to rationalize the denominator the same way we did it over here in the previous part. So negative times a positive, it's going to be negative 4 root of 5 over 5 times 5, which is 25, plus negative times a negative, well, that's what, positive, and 3 times 2, which is 6 root of 5, and in this case, root of 5 times itself, that's going to be 5. 5 times 5, that's 25. And in this case, 6 root of 5 minus 4 root of 5, that's going to give us 2 root of 5 over 25. Final answer for this exercise. All right, let's look at another type of example here. Okay, so in this case, let's do an example that has to do with establishing identities. You know, like what we did in the previous section. Well, we need to work on this right hand side and be sure that it matches the right hand side. So what are we going to do? Well, the most imminent thing that I'll look at is this cosine alpha minus beta. And that makes me think of using this formula right here, the second formula, cosine alpha cosine beta plus sine alpha sine beta. Okay, so I'm going to start by writing cosine alpha minus beta over sine alpha sine beta. Okay, and I'm going to write that as a cosine alpha cosine beta plus sine alpha sine beta. And then this is going to be sine alpha sine beta. Okay, notice we have a sum of terms in the numerator. So what I'm going to do, I'm going to split this cosine alpha cosine beta over sine alpha sine beta plus sine alpha sine beta over sine alpha sine beta. Okay, so look at this. Well, this one is going to go to 1 because that's simply a quantity divided by itself. But in this case, okay, pairwise, cosine alpha over sine alpha, cosine beta over sine beta, this is cotangent of alpha, and this is cotangent of beta, and this goes to 1, that's simply plus 1, which is exactly what we wanted to show, isn't it? That's what we wanted to show. Alright, so is that it for sums and difference formulas? Well, not really. Well, we can still do one for tangent. Alright, so we have a couple of formulas for tangent and their their differences, you know, sums and difference of angles involving tangent in this case, and we have these two formulas right here. So tangent of alpha plus beta is the sum of the tangents of each corresponding angle over 1 minus the product of those tangents, as opposed to the one with a negative sign. What changes is these two signs, you know, plus plus minus 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 plus. That's all that changes. Essentially, the formulas are exactly the same. So let's find this the exact value of tangent of 7 pi over 12. Alright, so that number 7, I'm going to write this as 4 pi plus 3 pi, because 4 and 3 reduce nicely to 12 in a way that the denominators are either 3, 4, or 6. In this case, they are going to be 4s and 3s. Okay, so that's going to be tangent of 4 pi over 12 plus 3 pi over 12. And well, when we reduce this 4 over 12, that's going to be pi over 3 plus 3 over 12, that's pi over 4. So these are angles again that are in the unit circle that we can very, very easily take advantage of and then evaluate this quantity. All right. Okay, so keep in mind, let's consider this as our alpha and this is our beta. So we're going to use the first formula, the one that has a plus, plus, minus. So tangent alpha plus tangent beta, that is tangent of pi over 3 plus tangent pi over 4 over 1 minus tangent pi over 3 tangent pi over 4. Alright? And all we have to do right here is simply use the unit circle and get those values. Tangent pi over 3, pi over 3. Tangent is going to be root of 3 over 2 over root of 3 over 2. Well, let me actually simplify those values on the side. So on the one hand, tangent pi over 3 will be root of 3 over 2 over 1 half. These go away, giving us a root of 3. On the other hand, tangent of pi over 4, for pi over 4, tangent is sine over cosine, root of 2 over 2 over root of 2 over 2 divided by itself. That is root of 2 over 2 over root of 2 over 2. This is simply 1. So this will be root of 3 plus 1 divided by 1 minus tangent of pi over 3, which is root of 3, times 1, which is simply root of 3 plus 1 over 1 minus root of 3. Alright, and in this case, well, we can leave it like this. It is fine to leave it like this, or if we rationalize the denominator, by multiplying by the conjugate of the denominator, well, this one I'll leave it up to you as an exercise. I mean, this is fine, but if you wanted to simplify a bit further, you should obtain negative 2 minus root of 3. Alright, and just to initiate that, you would multiply by the conjugate of the numerator and the denominator by the conjugate of the denominator. Alright, you should have done that. Either way is fine. Okay, let's keep moving on. So for example number 6, the identity tangent of theta plus pi equals tangent establishes that the tangent function is periodic with period pi. Wow, there's a couple of, this is with period pi. Like well, where are we getting this from? You might remember the periodic properties of the trigonometric functions. Well, sine is and cosine, they have a period of 2 pi. And in this case, tangent has a period of pi. So we're going to do the following. We're going to use this identity here again. Alright, so to prove this periodicity of the tangent function to be pi. Alright, so this is alpha, this is beta, and tangent of theta plus pi, it's going to be tangent alpha plus tangent beta. In other words, tangent theta plus tangent of pi. Alright, tangent of pi, that's 1 minus tangent theta tangent pi. Alright, but we have a problem here. Oh no, never mind, there's no problem here at all. Not at all. So tangent pi tangent of pi? Well, if we use the unit circle, we will go to pi, tangent, which is sine over cosine, 0 over -1, that's a 0. So tangent theta plus 0 over 1 minus tangent theta times 0. So in this case, this is going to go to 0, all right? And tangent plus 0 is tangent. And in the denominator, 1 minus 0, which is 1, and that's simply tangent theta, as we wanted to show. All right? So that's pretty much it for that example. Now, let's prove the following identity. All right. So there is there will be a problem here if we try to use the same identity over here. Let's not write anything in here. I'm going to write this somewhere else. Okay, so let me write tangent of theta plus pi over 2. And that equals, well, tangent theta plus tangent pi over 2 over 1 plus, minus actually, tangent theta tangent pi over 2. There is a problem here if we use this formula, and the problem for this is that the tangent function is not defined for pi over 2, if you recall from a couple sections ago. So we need to take a different alternative in this case. So in this case, what we're going to do is, on the other hand, I'm going to write tangent theta plus pi over 2 as sine theta plus pi over 2, because sine of pi over 2 is indeed defined not for tangent, over cosine theta plus pi over 2. And then I'm going to use, in this case, the sum formulas for tangent and for sine and cosine. Okay, so sine of the sum, let me put it over here. That's sine of the first part of the argument, sine alpha, well, sine theta, cosine pi over 2 plus cosine theta sine pi over 2. The whole thing divided by cosine. Well, I need to use the formula for cosine, and that I'd better put it over here. Cosine of the sum, cosine alpha, cosine beta, minus sine alpha, sine beta. So cosine theta cosine pi over 2 plus sine theta sine theta. Well, actually this is minus sine pi over 2. And let's evaluate this. Well, okay, so the only one we really need to worry about is cosine of pi over 2 and sine pi over 2, and then take it from there. So let's go to pi over 2. Pi over 2, cosine is 0, sine is 1. So where we're looking for cosine, this one is going to go to 0, and this one is going to go to 1. All right? And then this one right here is going to go to 1. And this one, the whole thing is going to go to 0. Because in this case, cosine of pi over 2 is 0 times sine theta is going to, the whole thing is going to get zeroed out. Same thing here. So we're going to have 0, or if you prefer, sine theta times 0 plus cosine theta times 1, and cosine theta times 0, and that's minus sine theta times 1. Alright, and in this case, well, these two guys go to 0, of course, and cosine times 1, that's cosine, minus divide, or actually minus in the front, and sine. And in this case, cosine over sine is cotangent, as we wanted to show. All right, end of proof. Okay. All right, for the last page, well, the last couple of examples, well, this one, I think this one is going to be a little bit lengthy, but well, let's. Where do we start for this example? So those are pretty cool examples, in which again those examples we put everything together, you know. So my advice for this type of examples is call this your alpha, call this your beta. We're gonna have a Cartesian plane for alpha and another Cartesian plane for beta. Alright, well, so in this case, what are we going to do? So, let's see. We establish the identity in which simply cosine alpha plus beta, and then simply, well, not that simply, we will do cosine alpha, cosine beta, and then minus sine alpha, sine beta. So in the end, we are going to evaluate this quantity based on the values that we obtained from these two identities. All right. So, well, in this case, we have that for alpha equals sine inverse of 2/3, which means that sine alpha equals to 2/3. Okay, so in this case, well, what are we going to do here in this case is evaluate this, create a point. In this case, this is y over r. Well, in this case, r is always positive, y has to be positive as well. So the point is something which is going to be the x comma 2 with a radius of 3. Okay, so we need to find the x. R squared equals x squared plus y squared. Okay, and then, well, r is given 3 squared equals x squared, what we want to find, plus y squared, which is 2 squared. 3 squared is 9, x squared plus 4, and then x squared equals 9 minus 4, that's 5. X equals plus or minus the root of 5. Okay, yes, we're being a little bit strict in the theory of solving quadratic equations, but in the end, because we are in the first quadrant, well, take the positive. Take the plus, take the positive, okay? Not the negative, because we're not working on a quadrant in which the x value is negative, all right? Square root of 5. All right. So we are basically we basically have everything solved for alpha. Let's do the same for beta. Well, inverse tangent of theta. Well, in this case we have a negative value, and we need to be very, very careful about the range for tangent. Where is inverse tangent defined at? So in this case, keep in mind that inverse tangent is inverse tangent only lies between negative pi over 2 and pi over 2. That is in the first and the fourth quadrant, right? So these 3/4 right here, when we establish this okay, for beta, I'm going to write it down here. Beta equals tangent inverse of negative 3/4. So that means that tangent beta equals negative 3/4. In this case, well, this is y over x. All right, tangent is y over x. So in this case, if we plot this point cannot be plotted in the first quadrant, because in the first quadrant everything is positive, both x and y. So we need to plot this in the fourth quadrant. In this case, y in the fourth quadrant. Okay, let me go back to section 7.1, I believe. Okay, let me check those notes real quick. I can show you. Okay, on page 5 of 7.1, if we go back to the arctan, the inverse tangent, this is valued only between negative pi over 2 and pi over 2 in the examples. If you remember, we did this region. In fact, maybe I should have shaded, but well, in this case we're assuming that we already saw that. But anyway, I'm coming back to this very specific piece of information. All right, so that being said, well, in this case we want y to be the negative and x to be the positive. All right. Actually, I changed the example. Well, I didn't choose the example in the book, because the example in the book, as I'm going to show you here, it does everything really nice with positive values. It does it with positive values, but it doesn't tell you what to do in a situation in which a negative number like this is given. So that's what I'm doing this example instead. All right, so in this case, well, again, we see how we're putting together that section in which we learned that tangent lies between negative pi over 2 and pi over 2. So we have to locate that point in either quadrant 1 or quadrant 4. And of course, there's no other choice than quadrant 4, because quadrant 1, again, like I mentioned a minute ago or so, it's a positive value. All values are positive. Okay, what's r? We need to figure out what r is. That's going to be, okay, r squared x squared plus y squared. In this case, r squared equals 4 squared plus negative 3 squared. R squared equals 16 plus 9. R squared equals 25. R equals the square root of 25, in this case plus minus, of course, if you want, but keep in mind that this is the radius of the circle, and the radius is always positive. Okay, R equals to 5. So we already have everything done. So for alpha, what do we have for alpha? For alpha, we have x, y, r. X equals root of 5, y equals to 2, and r equals to 3. For beta, x equals to 4, y equals to negative 3, and r equals to 5. Okay, so we're ready essentially to get all this. All right. Cosine alpha, cosine, keep in mind this is x over r, cosine x over r, sine is y over r, Well, depending on the alpha, be careful with the alpha that you choose. Okay, cosine alpha, I'm going to go with the first diagram, in fact, with this number summary here. So x over r, root of 5 over 3. Times x over r, but for beta, 4 over 5. Okay, yeah, that 3 looked a little bit messy. Let me fix it. Minus, okay, that's a 3, of course. Now I'm gonna go with sine alpha. That's y over r for alpha, 2 over 3. And y over r for beta, negative 3 over 5. Okay, all we do is simplify these numbers. Well, that's 4 root of 5 over 3 times 5, which is 15. Negative times negative, that's a positive. Plus 2 times 3, actually, you could divide out these 3's if you want. However, well, I'm going to do the following. I'm going to do 6 over 15 to later simply combine into one single number. 4 root of 5 plus 6 over 15. Final answer to this exercise. All right. Let's do one last example, and this one has to do with writing expressions in terms of u and v. Well, writing trigonometric expressions in terms of that do not contain trigonometric functions, just functions of u and v. Okay, so again, this guy right here is alpha, this guy right here is beta. Sine of alpha plus beta. Let's recall the formula for sine alpha plus beta. Well, where's my formula sheet? Where's that page? Oh, it's right here. It's right here. Sine alpha cosine beta. And plus cosine alpha sine beta. Alright. Okay. How are we going to deal with this type of expressions? Well, okay, let me set up an equation for alpha equals sine inverse of u, while beta equals cosine inverse of v. In other words, sine alpha equals u or u over 1. Remember that u over 1 that we did in the previous section? Cosine beta, or a couple of sections ago, not in the previous one, that equals v over 1 as well. Okay, let's define sine as y over r and cosine as x over r. Okay. So we're going to look at a point in which, well, in this case, we don't have any negative values, only v's and u's. So we don't have an idea of what the values are. So we can safely assume that these are going to be really, really nicely in the first quadrant. All right. So in this case, well, let's see. So we're going to look for a point in which x, which we need to figure out what that is, comma y, which is u. And the radius r is 1. Okay. So r squared equals x squared plus y squared. And r squared, which is 1 squared, equals x squared plus y squared, which is u squared. So 1 squared, which is 1. I'm going to solve for x squared. That's x squared equals 1 minus u squared. And x equals the square root of 1 minus u squared. Let's do the same over here. So this time I'm going to go to a point in which x is v this time, and the y coordinate is the one that we need to figure out what that is. So r squared equals r x squared plus y squared, and r squared, well, what was r? Also 1. 1 squared equals v squared, because that's what x is, plus y squared, and then y squared equals 1 minus v squared, very similarly actually. And y equals the square root of 1 minus v squared. Alright, so that's the square root of 1 minus v squared. Okay, so we have everything that we need. R, x, and y. R, x, and y. Okay, so sine of alpha. Sine alpha, well, it's we are given sine alpha. Sine alpha is u over 1. That's simply u over 1. U over 1 is simply u. Cosine b, that's actually given, is v over 1. I'm not going to write v over 1. I'm simply going to write v. And then plus cosine of alpha. Cosine of alpha is the x value in the first diagram. That's the square root of 1 minus u squared. And sine beta, that's from the second diagram. Sine is the y value. In this case, simply the square root of 1 minus v squared. And in this case, I mean, you can leave it like this, of course. You can leave it like this, or put everything inside a single radical plus the square root of 1 minus u squared times 1 minus v squared. And that's our final answer. And this is a good place to quit this section. I'll see you in the next video.